Hey guys, welcome back. So we're going to talk about statistical concepts today, obviously. There's a couple things that I want to share at the outset about what we're going to cover here. So first of all, this is going to be part of kind of like a 2 to 3 to 4 week series, depending on how you're consuming this stuff. It's going to be a series of videos. And the reason that is because a lot of this stuff is going to be building on each other. So we're going to start really basic stats, nothing that you guys can't handle in terms of like learning what the mean means, like averages. So this is something that all of us at this point can understand. But the reason we're going to start there is we're going to start at the very basic. We're going to build until we really get into what are test assessment results like and how do we understand them. More importantly, later in the semester, we're going to talk about how do we not only understand them, but then communicate those back to other people, translating it out of statistical language into common parlance. So that's kind of our goal here. The other thing that I want to tell you is that, well, there's a couple things I want to say. One of them is that our goal here is not to become experts in understanding the underlying math and how statistics is, how we use the math to take data and then do something with it and then change it and then come out with all this research. We're not understanding how to do research. We're not understanding how to build assessments. We're understanding how to consume both of them. So we're going to be come out of this hopefully saying, okay, I know what T-scores are. I know what percentiles are. I know how to understand an IQ score and understand just the basic level of how does this translate to what some client might need to know. So that's kind of the level that we're going for here. Many of you have taken a statistics class where you went back all the way to the beginning to the mathematics and you're adding numbers and you're calculating them and all that kind of stuff. And I did that in my training. And I just don't ever do that in my life. And so we're going to try and take kind of a practical approach at this and say, what do we, oh, my head's in the way. Take a practical approach to this and understand what do we actually need to know in order to do some translating of mental health data and testing and assessment to your clients. That's really the ultimate goal here. Part of that too means that we're going to hopefully take some of the anxiety and fear out of how these statistics work and how they operate. We don't really want to instill fear in everybody and be like, we're going to do math here and you should be super anxious about that, because a lot of us, frankly, are nervous about the math. And so we're going to go through some of the math only to justify how we get to numbers later on. And it's the numbers later on that we really need to understand. One of the things that I did in my training was I went way back into I mean, we had to calculate everything. You take raw data and you calculate it right from the ground or from the participants in like a research study or something, and then you calculate it all the way through your correlations and your post hoc analyses and all that stuff. But we just don't need to do that because for a couple of reasons. Frankly, you don't need to do that in order to understand what the end result is, and computers do that all for us. So we're just not there. If you want to go get doctoral degrees or some other kind of thing, you can absolutely go understand the science and math. It's fascinating. It's wonderful. It's super nerdy, but and it has a very important place. If you can do that, you'll be one of the minority in the clinical world that can do the research that we desperately need. So this is not me saying it's not important. It's saying it's important for another time. So take that into consideration. So I'm actually going to see if I can boost up my camera, get my head out of the way of this, the captions up above. So sorry about that. Okay, now I think I got my act together. So here we go. I am going to talk about some of the slides here first. And then, by the way, what we're going to do is we're going to jump into the textbook. I have some things out of the textbook here. You can't see it, but it's right down here on my desk. And we're going to talk about that too, but we'll save that for just a minute here. So again, we're just going to, let me recap a couple things, starting with number one here. A statistic, when we say that word, essentially what we're saying is it's just a numerical representation of information. In other words, we want to take some social construct out in the world and then put it into a number that we can then manipulate and do something with. Because if we can do that, then we can understand information that we can't see. It's sort of like saying, if you have a microscope, you can do more than what your naked eye has available to it. In the same way, we have all these social things that happen around us and things that happen inside of our heads that we frankly just don't understand until we have a bunch of numbers. And once we can, or information, I'll say data of some kind. Once we take that and manipulate it, do something with it, then we can understand it a little bit better. Now, there's two ways that we do that. One of them is that we can understand over time. In other words, how have we historically progressed to the point we are, or how do people develop from baseline to symptom, or from symptom through intervention to back to baseline, just that kind of stuff. It's through time, and we can't really always easily observe that. The other thing is, especially with one person, maybe, with a couple people, probably, with a whole huge amount of people, over time, like thousands or hundreds of thousands of people, that takes another kind of perception, and we just don't have that. We can't fit that many numbers into our head and do anything with it. So we use statistics to help us with that over time. The other thing is over space. If I want to see people in my clinic, great, I can do that. If I want to see people across town, I could probably send out surveys and do a bunch of stuff. But if I want to understand how do all Americans or all people or all Europeans and Westerners or Easterners, whatever the thing is, if I want to do that over a large space, that's when I have to gather a large amount of data, and that's when we have to do something with it to condense it down into meaningful chunks. So all of this stuff that we're going to go through here, all of these statistics, is just taking something that's maybe a massive amount of data. We're going to start small, but it applies to large amounts of data over time and over space, and we're going to condense it down into meaningful parts. Once we do that, we can manipulate it to turn it into something else that's different entirely. Take, for example, a bread baking recipe. We have our flour, we have our yeast, we have our water and sugar and all kinds of, I don't know, oats and barley and whatever the crap you put in bread. I don't know. I used to try and make bread, and now I don't do it anymore. But imagine you have all those things, right? We know what wheat looks like, and then we know if you smash it with a hammer or run it through a mill or whatever, it turns into something else, and we're like, oh, but flour is different than wheat. It seems more useful. You can't just chew on a stalk of wheat. But flour, you can kind of do that. It's more edible in that case, right? And if you're my son, whenever we make pizza at our house, we take the flour and you mix it all up in the bowl, and he just sits there and licks the flour. It's disgusting, but he does it. So, but it ultimately becomes differently consumable, right? That's the point. And then if you add water and yeast and put it all together and let it sit in a bowl, it becomes something that's even closer to like raw bread. Put it in the oven, and you see there's all these processes of mixing and changing the chemistry of it, frankly, into something that ultimately we love. And that's what we're going to get to here. Is we're going to start with numbers. They look pretty rough, like the wheat, and then we're going to do some things to them, change them, manipulate them, and then turn them into ultimately something that's digestible, metaphorically and, well, metaphorically. So that's the goal here, okay? So that is going to take us a couple days to get to that, or a couple lectures here. So I'm just kind of expanding on point one here. The other thing to say about this is data is meaningless if not formed into something understandable. Taking our analogy that we just used about the bread, it's that the wheat is kind of useless unless you pound it, unless you add it to water and yeast, and then put it in the oven and bake it. You can't really do a whole lot. I mean, you could probably eat the wheat, but it's not quite the same thing. And because the chemical process changes its properties, it's not consumable in the same way. So that's all we're talking about here, is we're taking these just raw data and raw numbers over time, over space, all kinds of people, all kinds of different social situations, and changing it and manipulating it into something that's consumable and useful, or understandable in this case. So another thing that we should know too, remember we're talking about a large swath of kind of data, and it's just very general. When we say things like building assessment based on how assessments are validated and all that kind of stuff, that's one camp of what we're trying to understand here. There's also using data in research, and that involves assessment, but it's just a different kind of stuff. It's a different kind of manipulation of variable. So we're going to be kind of talking about both of those a little bit. More so, we're going to be talking about assessment usage of data and that kind of stuff. Occasionally, we'll dip our toe into what is research and how is it formed, specifically when we're talking about things like correlations, because we might give an assessment on something like depression, and we have a couple numbers that lead up to one variable. How much is your depression? Like, what's the number? How do we quantify that one variable? With correlation, that's two variables. That means if I change the intervention, what does that do to the dependent variable? Does it go up or down? In other words, if my intervention's good or it works, is the depression going to go down? We would hope so. If we're measuring something else like resilience, it might go up. And we'll get into that a little bit later. So we're talking about lots of different stuff. as it relates to something like descriptive statistics and inferential statistics, excuse me, I'm going to say that word tons and I'm going to start tripping over it probably. Descriptive statistics describes something in the world. It just says, here are the amount of that thing, here's what we do, here's what the average of that thing is, here's how we can quantify it and measure it, okay? It's just describing something. Inferential statistics says, well, if we know a little bit about that thing, we can infer something or project or anticipate or any of those kind of like future tense kind of words. We can say, here's something else we can understand about it. A classic example is when during like political season and people are all over the TV saying, so-and-so is ahead in the polls. Well, how do they know that? Like, they don't know everybody's thinking, right? However, what you can do is if you do some, and these are terms that I'm not going to explain too much, but hopefully you remember these from your undergraduate days or whenever you last took your stats class. If you have a representative sample, same amount of men and women, same amount of people from the South and the North, same amount of people from this cultural background, that cultural background. If you get a good representation of all the people, if you have a smaller sample of that, you can infer that we can just expect that if we doubled our sample size, we'd probably get the same result. If we measured every single American in the entirety of the US, if that small sample is representative, then we can assume something about the population. That's what inferential statistics is. We are not going to do that with our assessment data. We're not going to be like, well, your son scored, a 50 on this test, therefore we can infer that in 10 years we're just not going to go there. That's just not what we're talking about. But you might hear those different terms and be like, how does this fit? Well, it fits, but somewhere else. We're just not going to care about it for the time being. The other thing that sometimes we'll start out with, or sometimes people start out with, and they explain statistics. If you want to start at the bare bones, very beginning, there are these scales of measurement: nominal, ordinal, intervals, ratio, all that kind of stuff. That's how I started learning statistics, and I had no freaking clue why it mattered until I got to the end. And when I got to the end, I was like, oh, okay, when you do an analysis, this kind of data has to be handled a different way. It has different kinds of mathematical formulas that apply to things like, for example, nominal data. A word with no numerical representation, that would be like a client satisfaction survey. How good was your therapy? Good, pretty good, freaking awesome. Well, there's no number for freaking awesome. There's no number for good. So you just have these words, but those can be then turned into numbers, but they have to be handled a special way. That's a little bit different than if I say like, who scored the highest on the test? Well, the highest is going to be one person, and a little bit below them is going to be another person, and so on. And that rank order number is just different kind of information. So we're not going to go into this. We might bring it up a little bit later. I'll just sort of make a passing comment about post hoc analyses and that kind of thing. But by and large, we're not going to start talking about these things. It's here if you want to look at it. It's in our textbook if you want to read about it. It's important if you're going to be doing the math, but for our purposes, I think we probably don't need to care so much. One thing you may want to know a little bit about this, the reason you may want to know a little bit about this is if you're doing any kind of program evaluation or you're trying to collect data for the purposes of funding or something, you're not going to need to use the mathematical words likely, but you may want to spend some time thinking about how am I going to get the best kind of information based on what I'm trying to understand. But that's a whole different level of evaluation and assessment, and we're just not going to go there right now. In fact, many of you will have a different class called something like research and program evaluation or something like that, where you may go into the terms, but you're going to use that information a little bit differently. So I'm talking about all this to help us pare down the scope of what we're attacking here. Not attack; it's a dumb way to say it. Of what we're trying to grasp. When challenging the scope of it so we don't feel like, oh my gosh, there's so much to know. Well, we're going to limit that down. That's the point. Here are a few things we're going to talk about. Frequency distributions, those you guys probably know. We're going to fly through that pretty quickly. Measures of central tendency, again, pretty basic. And then we're going to start doing our build. I mean, all these things are going to be building, but we all know what a graph is. We can make one. If you go into Excel and you add all of your grades up, you can make a graph for, which grade is the highest in which class, whatever. Like, you guys can handle it. You can do it with a box of crayons. It's not a hard thing. Measures of central tendency. Most of you know how to evaluate the mean. Some of you are going to need a refresher on what the median and the mode are. That's okay. We'll go through it. And then it starts to get a little bit trickier. Measures of variability. Well, I've heard the term variance or standard deviation, but what does it have to do? Well, what it has to do with is we have data, we manipulate it, turn it into a measure of central tendency, then we manipulate it more, turn it into variance, standard deviation. Ultimately, then we can come up with these things called standard scores, which that word is not here, but again, remember, wheat, flour, yeast, dough, bread. That's what we're going to go through this transition, and this is kind of the flow of that transition. So we'll talk about some of these other more complex ideas like correlation, regression, factor analysis. I'll explain a little bit about what they are briefly, but we're not going to go into those in detail, frankly, because most of these have to do with research, which is not something we're going to cover a ton of, or they have to do with test development. Again, not something we're going to cover a ton of. What you will want to know is how to understand how a test was developed at some point. In other words, if you're going to tell people like, well, this is what the information means, sometimes you'll have to dip a toe into, well, here's how the test was developed, so here's what the normative data means, something like that, and then you can explain how that relates. That's a little bit later, and that goes into each individual test by itself. So we're not going to cover that in great detail. Okay, now that we've got the groundwork, we're 16 minutes in already, and we've got the groundwork, let's talk about some of the terminology. This is something else I didn't mention, but I'll mention it now, which is statistics has a whole different language that comes along with it. It's like, I mean, quite literally, it's almost like learning a whole different language. What is this thing right above my head? What would you call that? A bar graph? Probably. That's probably what most of the world would call it, but we call it a histogram. It's just another name for it. It's a fancier name. Why does it have another name? I don't know. It's just like saying, a doctor or a scientist might call a common flu by some other strain or some more detailed thing that's more scientifically accurate, but the rest of us, we just call it the flu. For our purposes here, especially in terms of understanding it and then translating into language that people know, we're going to use words like the flu or the bar graph. That's about all we need to know, I think. So there are times when we'll have to talk about very technical language and other times when we have to simplify it down for the purposes of ourselves or clients. But that's what we're talking about here. Now, when we start at the very beginning, you guys all know how to make one of these. And by the way, a frequency polygon, what would you call that? Pause the video, say it out loud, whatever you want to. Okay, I'll pretend that you did that. I call it a line graph. There's a bar graph and a line graph. It doesn't need to be super fancy, but these are the fancy terms we use for these. So what these are good for, though, is they're good for allowing us to take some information and then manipulating it into visualizing. Now, let me show you something really quick here. If I turn on my camera and we go to page, by the way, this is going to be kind of blurry. I did my best to make all of this look more clear and bright and that kind of stuff, but this may be the best I could do. So page 93 in our textbook, by the way, this is the book we're looking at, 9th edition. And these are the guys and gals that wrote it. If I take our book and we look through here, we have a bunch of scores, okay? This is the Strickland locus of control scale. Doesn't really matter for our purposes. We're not going to go into this example specifically. But here are a bunch of scores. We have 15, and that score was scored once. That was the frequency of it. 14 once, 13 once, etc. And you guys kind of get how that works. That's fine, but it's kind of a little hard to see because you have 1, 0, 3, 2, 4, 5, 4, 3, 1. But if I want to take those numbers and rearrange them into something that's maybe more understandable, I could totally do that. All right. And then, I mean, there's lots of ways to rearrange and manipulate and organize. But the whole point that I'm trying to get at here is that a bar graph and a line graph are visual reproductions of information in visual form. And that can be really helpful in many, many ways. So I think you guys get that. Pretty basic. We don't need to spend too much time on that. I know I didn't cover what those sub bullet points or whatever were, but just those are reasons why we might use it. To see clusters or concentration, also see patterns, that can be really helpful. High peaks or low lows. We'll show examples of what assessment results look like, and we'll see that line graph in practice. In fact, I wonder if I can do this really quick. Yeah, let me look at this one. We'll come back to this and revisit it a little bit later, but here's an example of the Symptom Checklist 90, or the SCL 90, the revised version, so SCL 90R. And this doesn't typically come with these lines. I can't draw straight lines, so sorry. But I tried to draw my like half curvy, not very straight lines. But I connected those dots, and the reason for that is just so that we can kind of see the pattern of presentation of this client in terms of their symptomology. So we're not going to spend a ton of time on this. See if I can get this up a little more. But you can kind of see like, well, I can see now the peaks. I can see the high ones. What's high? Well, it looks like for this person, maybe the phobic symptoms, or the phobic symptom cluster, are probably higher. And if we know some things about symptomology, we know that phobias are kind of in the category of anxiety disorders. All of a sudden, we can start putting in our heads together a picture of who this client is and what's going on. Not ironically, the anxiety scale is high as well, and you'd probably kind of expect that. It'd be very weird to look at this and say phobias are high, but anxiety is low. Well, what the heck does that mean? That means when someone gets scared of spiders, they don't actually freak out about it. But isn't that what a phobia is? So, in other words, seeing it in picture form, pretty helpful. Okay, let's move on. Back to our thing here. And back to the next slide. There we go. Okay. So, again, building blocks. I'm not going to read off the top thing, but you guys probably know what the mean is, and you know how to get to it. In fact, we're going to look at the math in a little bit and say, how do you calculate the mean? That's probably way more elementary. You're like, this is graduate course? You kidding me? We have to talk about the average and learn how to do the math? Well, kinda. You add up the scores and you divide them by how many scores there are. That's relatively simple. However, there are certain situations where you may not want to use the median. And we're not going to talk in great detail about these, but there are some really important times when the median has been used in my world, and so I'll explain it to you just in case it's helpful. But here's a classic example. Let's say I want to understand what the average income is in my city, wherever I live. And I go around and I start asking people, I say, how much do you make? And they say 20,000. And I ask another person, they say 40,000. And I ask 10 more people, and it was somewhere in between 20 and 40. I do the math, and I find out that out of all the people that I asked, maybe all 10 people that live in my village, we'll just pretend it's a small place just for the sake of not making our brains hurt too much. And I find out that all of them make probably an average of about $30,000, right? Add up the 20s and the 40s and divide them by however many I asked, and 30,000 is extra. Well, let's say our little village is the perfect vacation destination, and LeBron James decides he's going to make one of his mansions here. Well, his income is exceedingly higher than $30,000. I don't know what it is. I don't care. But let's say he comes and moves into town, and I say, okay, well, if I'm going to be technically accurate, I want to ask everybody in town so that I get a good representative sample, right? But if I incorporate his income, it's going to really skew that number. In other words, I'm going to then get some wild number like, well, everybody, the average income is 100,000, but that doesn't really represent what the community makes, right? So the reason we use the median, or the middlemost score, is it cuts down on those outliers, either exceedingly high numbers or exceedingly low numbers. It would be like saying, I have a clinic and people are typically, they have a depression score of, I'm just going to make a wild random number, say like 13. Except for there's this one guy that brings it down because his score, he comes into counseling and he's not depressed. He says he is, but he doesn't have any of the symptoms. And so his score is 0. It just doesn't really help us understand what the majority of people live like, or how they feel, or what the social thing is that we're trying to understand. So anyway, the median, that's what it's for. It can be used in different ways. But for the purposes of what we're talking about here, for the most part, we can kind of set that aside. The mode, we're not going to go into that one either, but the most frequent score, if I were really just doing some basics, understanding descriptive statistics, I might want to know why 15 people in my 30-person class got the score of 75, and I might be like, oh, you guys are all friends. You're cheaters. Just kidding. I wouldn't assume that. But it might give me good, valuable information as to why that number is coming up so frequently, right? So there are circumstances which it might be valuable and useful, but we're going to put it aside for now because the mean is really what's going to be the most important. Another note about some stuff in the book. By the way, my screen here, I'm going to tweak this just a little bit so I can, oh, that doesn't help. So you can see the bottom. There we go. In the book, it talks about these things called skewness and kurtosis, and those are really important when you're if you have another sort of well, I'm going to use some terms here, don't worry about these, but if I have a non-normal data set, in other words, if it's high or if it's low, or there's something really unique going on with that data, we might have a normal curve, and we'll talk about the normal curve in a second, that's leaning to one side or the other, or it's really peaky or really flat. We're not going to cover that kind of stuff. Scientifically, it's important and valuable, but we're not going to dig into that level of detail because, again, we want to get to the end of what does an assessment report tell us, and how do we then talk to clients about that? How does that inform our clinical work? So we're going to skip over most of that. Another thing about symbology. Remember when I said it's like learning a different language? Let me show you something else. Let me see if I can get to this fast enough. We're going to talk about some of the math that goes along with this. And there's all these different symbols. So not only is there different words, not only is this different language, but then we have all this Greek and English and numbers and all this stuff. And so I just want to break down maybe if I can, some of the mystery, so I can get my camera fitted a little bit better. We're going to break down some of the mystery here. Now, this is probably hard to see, and we're not going to really worry about that. This is ultimately a formula for standard deviation, and there's all these weird symbols. So let's see. I'm not going to dig into standard deviation just yet. In fact, let me see if there's another slide here that talks about it. Yes, we'll talk about that next. Okay, actually, tell you what. I know I'm being goofy here, but let me switch this around, and we'll talk about this stuff first. So let's pretend that I have a mean, or I have an average. I poll all the people in a class. Let's say in this class, I give everybody a test, and some of you score 80 and some of you score 90, and then I take the average of all the scores and I get 85, just round number. Doesn't matter what the test is for. But I want to know how big the variance is. What does the variance mean? It means how much those scores differ. And a test of 80 to 90, average 85, that kind of, it's interesting, you know, like 5-point difference between most people, or 10-point range between most people. However, what if I had a test and some people were scoring 50 and some people were scoring 100, and it still averaged 85? Well, the mean would be the same, but there'd be a bigger variance, or how much scores vary from the mean. That might tell me something important about the kind of people. Maybe it's like the people in class are learning nothing and all the online people are totally nailing it, right? That would give me some kind of story about the data that I could actually use and would be useful for me. So that's what variance is for. And so in order to go from the mean, we have to first find the variance to decide how different they are than the mean. And then we're going to go understand something about the standard deviation. This is one that we're going to talk about a fair amount. So we're going to skip over, look at the math, then we'll talk about the standard deviation, and then we're going to use it over and over and over again. But this is a confusing one that usually gets a lot of people. But ultimately, that's going to help us know what we need to know to understand assessment results. So we're getting closer and closer here as we go to the end result of looking at actual test scores. So hang on and bear with me. So let's take a look at how we calculate that and what that's for. By the way, there are a few other steps in the mathematics that I'm not covering, but I'm not going to go into that in great detail because I don't think it's necessarily important. If you want to do the math, like I said, go for it. It's your prerogative, but we're just not going to do that. So, in fact, let me see. I'm going to move my camera around here so you can actually see this a little bit better. Okay, so let's talk about the symbols first because I promised I would do that. First, let's look at this. So we have a small s. That small s stands for standard deviation. And by the way, a lot of these symbols mean the same thing. If you see a small italicized s, it's almost exclusively going to be the standard deviation if you're looking at statistical formulas. So there's that. What is this big giant wiggly thing? That's called square root. Most of you remember that probably from your high school math classes. And then there's this other one that's a little, let's use this one for example down here. It's hard to see it, but it looks like a is it backwards? No. It's an E. It looks like an E. It's not though. I'm gonna kick myself for this. I shouldn't even say it out loud, but I want to say this is the Greek letter epsilon. You guys Google it really quick and tell me how wrong I am. Forget, but it's a letter that means the sum of. And then this X right here, the X, it just stands for each individual score. So here's our scores. Let's look at these. We're ultimately going to take this and understand what's going on here, because in our sample here, we want to figure out what's going on with number 5. This kid number 5, he got 62. But if I look at this score, how many, does it tell us how many, what the highest score possible is? I should probably know this, and I don't. Some of us might look at that 62 and just make the assumption that we're talking about 0 to 100, but not all scores are like that, because this could be a 0 out of 85 kind of score, that then 0 being the lowest, or maybe it could be 50 is the lowest. We just don't really know. So if we assume it's 0 out of 100, that 85, we're like, oh, he looks pretty good because he got like a B on the test or whatever. And this kid got a D, so therefore it's not good. However, we don't know that. And so what we're trying to do here is say, how do these scores compare? How do we understand them in a way if we don't know what the highest score possible is? That's what we're going to ultimately do here a little bit. So, so we have X is by itself, it's each of these individual scores. So we're going to plug in, by the way, the sum of all of those scores is 85 plus 92 plus 87 plus 74 plus 62. That's what that means. The N is how many scores. By the way, this is just the formula for understanding the mean, and the symbol for the mean is X with a line over it. Okay, so X is an individual score, X with a line is all the scores averaged. That's what we're trying to understand here. Here again is the formula for average. You take them all, you add them all up, you divide them by 5 because there's 5 scores, and you get the score of 80. So now we know what the average is, okay? Step 2 is, and I'm going to fly through these steps because these are the ones I don't really care about for our purposes here today, but we're going to subtract each one from the mean, and that's just part of what you have to do in order to get these scores. So you don't have to remember that. We don't have to watch it. We just know that that's going to happen for all of these. In other words, how much higher is 85 from 80? It's 5. How far away is 92 from 80? It's 12 points away. See how that works? And we just do that for the rest of them. And then you have to do this thing called the sum of squares, and the only reason to do that is because we can't really deal with negative numbers. We have to somehow turn these all into positive numbers. So if we square all of them, they all turn into positive numbers. You can see that here. And then we have to do a little math to add those up. In other words, the sum of the squared differences. What does that mean? It means we have the difference up here, we squared them, and then we have to add those squared differences here. Again, language, we don't care, but that's what it is. And if we do that, then we can divide them by this other thing, the number of test scores minus 1. And we're not going to talk about what that means. In some kinds of statistics, you might see this referred to as like degrees of freedom or something like that. But we're not going to talk about that right now. We're just going to leave it like, just pretend that you have to do that and you follow the rule and you don't have to understand why. So for today, anyway, that's what we're going to do. So you do that. You divide by 4 because we had 5 scores. Remember, n without the line over it just means how many scores do we have. We minus 1, have 4. So divide that sum of squared differences, or sum of squares. Sometimes it's referred to simply as sum of squares. And divide it by 4, and you get this number. Now this number is the variance. Now what does 144.5 have to do with anything? Well, I don't know. It's just the variance, and what we know is that that's what that is. It's just if you took all of those scores and added the differences up, the higher the difference, it means the more these things are spread out from each other. But again, it doesn't really tell us much. Remember when I said we're going from wheat to flour to dough? Well, what is dough? You still can't really do a whole lot with it. You're not going to eat dough raw, probably. It doesn't taste that good. It's not really consumable, but it's an important part of the process. Same here. So don't worry about too much about what that number means. we just need to get there in order for flour to turn into bread. And then if you just take the square root of the variance, that's easily how we find the standard deviation, okay? So we're going to talk about standard deviation. I'm not going to cover a ton of it right now, but the thing I want for you to know is that this is an incredibly important number, and you'll see why in a little bit. And what that essentially is that standard deviation allows us to understand how individual scores relate to other scores. So going back to our book here, remember when we said this 62 relates to these other scores somehow, but if it's not on a scale of 0 to 100, we're not really sure how that relates. However, once we are equipped with understanding what the mean is, we know the mean is 80, and we know the standard deviation is, behind my head, sorry, we know the standard deviation is 12.2, all of a sudden we can glean some information out of that. What kind of information can we glean from that? Hold on to that thought, and we'll get back to it. I'm not going to talk about it just yet because I have a few other things that I want to cover and just explain, but we will get to it, I promise, okay? So, in fact, let me just look forward here real quick. I'll bring you guys back with me so you can see what the heck I'm doing. Yeah, okay, so what we're going to do is I'll give you a little foreshadow, but in the next lesson, we're going to pick up on this and talk about it a little more. In fact, I think actually what I'm going to do is I'll give you a little teaser about what it is, and then, but I'm not going to tell you the whole story, so you don't have to fully understand everything, but then I'll come back and I'll fill in all the gaps. So let's do that now. I'll give you the teaser. So I'm going to flip forward here actually a little bit further, and I'm going to skip to chapter 6, and we're going to go all the way to, is that the best one? We're going to talk about okay, next page. We'll just talk about it right now. It's not on my slides, but who cares? Okay, some of you probably have seen this. This is, well, actually, I hope all of you have seen this. This is called our normal curve. The normal curve says, well, how do I explain this in a way that's not going to be wildly confusing? The normal curve means if I were to assess everybody in the world on this same scale, or whatever the test this is that these students scored on, if I did that for everybody, we would be able to find out the average. And with the average, the great majority of people would score very close to average. In other words, all of the people, if we took everybody's scores and we put them on this line and we said most people score here, there's going to be a very few really smart people, and there's going to be a very few people who did not do that well on the test. However, the majority of people are going to fall very close to average, and we just know that. It's kind of like scientists have taken samples and collected data for a long time and found out that, we can assume that if we collect enough data, it's going to approach some distribution shape like this. It's called the normal curve. This is what's normal, or what normally would happen if we had enough information. Knowing that, we can then learn some things about this kind of normal curve and how an individual score relates to it, okay? So let's plug in some data so we can understand using the symbols we have here. And by the way, I'm gonna see if I can get a pen here really quick. I wrote in some few things here just because I've taught this same lesson a couple times, so some of you may not see these numbers in here, but it's a little hard to read that because it's maybe blurry, and maybe if you're on a small screen. But right here in the very middle, we have an X with a line over it. And if I were to pause and say, what the heck does the X with a line over it stand for? Well, you would say, oh, we just looked at that. That's the mean. I know what that is. So let's plug in our number. What's our mean? Here we have it right here at the bottom. The average for this distribution of scores right here is 80. So we know that the average is 80, the number 80, okay? Now we're getting closer, remember, just to keep us on track, we're getting closer to understanding what 62 is and how that relates. And we know that our standard deviation is 12, okay? So here's the thing you have to understand about the normal curve, and this will be really, really important for you to understand later on. So this is something you'll just kind of want to get familiar with and kind of memorize, I guess. We know that a certain percentage of all the people are going to fall somewhere between 1 standard deviation above the mean, or +1, and 1 standard deviation below the mean, -1. So we know that just because of doing this many, many times, and we know the science, that 34% of people in a normal distribution are going to fall in 1 standard deviation above and 1 standard deviation below, same thing. So if we combine those two, what these numbers down here are telling us, that 68% of all people are going to fall within 1 standard deviation above. I'll do it this way so it fits this graph up here. 1 standard deviation above and 1 standard deviation below. Okay, I'll say that again because we're going to say it again a couple times. 68% of all people in any distribution are going to fall within 1 standard deviation above the mean and 1 standard deviation below. Okay, we don't know what that means yet, but write it down, keep track of it. Likewise, there's going to be another bunch of people that score between, the amount of people that score between 1 standard deviation above and 2 standard deviations above is 13.5% of the entire population. By the way, all these numbers should add up to 100. And these are, they're actually different numbers. It's like 13.6 or something like that. Sorry, 34.6. This is sort of round numbers. But if we were to add all these up, all those people that were part of that data set, they would all add up to 100. These just help us know what percentages of people are, or things or data, whatever it is, what percentages are falling underneath this normal distribution. Okay, this is where people kind of start to get confused and where I got to be careful about the language that I use. So all these percentages are telling us are something about the area underneath this normal curve. Okay, so like there's a lot of surface area under here, and there's a lot of surface area under here. If we could somehow calculate this little tiny chunk of surface area, which accounts for 2%, and this little tiny surface area that accounts for 13.5%, and we were to add all these up, well, we'd find that this chunk here is 34. If we were to add these two together, it's 68%, and so on and so forth. If we added this one plus this one plus this one plus this one, that would all together account for 95%. Another way to say that, again, I'll repeat myself a little bit here, 68% of the entire population of this distribution is going to be within 1 standard deviation below and 1 standard deviation above. 95% of all distributed scores are going to be within 2 standard deviations below and 2 standard deviations above. Okay, now let's figure out what the heck does that even mean. Okay, so again, recall back our average or our mean for that the 5 people here. These dudes and dudettes here, we have a mean of 80. And remember what our score was? 62. Well, what we're trying to do is we're trying to understand, where does that 62 score fall on this distribution? That's what we want to know. How does it, is this person like way above the average? Well, we know they're not that, but how far below can we understand this person to be? So the thing that's important, what we know is, remember, what does this negative number 1 mean again? That's the standard deviation, 1 standard deviation. And we figured out what our standard deviation is, right? We know that it's 12.02. Let's just use 12 as a round number for now. It doesn't really matter. We'll just pretend it's 12. Well, if I take 80, or my mean right here, and I subtract 12 to find out what this number is, that means I know what 1 standard deviation below the mean is. I can figure out what that score is. It's 80 minus 12 is 68, right? So I know this number is 68. Where did our kid score on this? Well, he scored 62. So this would be something like 68. And then if I were to find 2 standard deviations below, I would minus another 12 or subtract another 12, which would be 46. I was not stellar at math, but you guys you either laugh at me or scream at your screen if I got that wrong. So 68 minus 12 is 46, right? No, 56. This is embarrassing. 56. So 56 would be this number right here. 2 standard deviations below the mean would be 56. 80 minus 12 minus another 12, we're talking 56. and our kid scored at 62. So if we were to like split this up and break it down, this is not an exact number. It's not exactly halfway through because, again, we can't just assume it's half just because it scores, because the number, it has more to do with the area, distribution area. So this isn't exact science here. But if we had the number 62, right? Yeah, 62, and we know it falls somewhere between 68 and 56, we could say, if we were to then to add up these percentages, split this one in half roughly, because it's roughly half. 62 is roughly half, somewhere between 56 and 68. And we were to split our 13.5 in half, we could maybe just guesstimate that the surface area of this would be something like 7. We'll just round number it here for simplicity. It would actually be like what is that, 6.25, something like that. 6.75, sorry. If we were to do that and we added 6.75, we'll just say 7 for round numbers to make it easier. Take that surface area plus this surface area, we could say, well, he falls somewhere in the lower, we're getting close to understanding about percentiles here. We could sort of figure out what the percentile is. And that's kind of the next thing that we want to get to after we go from variance, standard deviation to percentile. Okay, this is when people say, dude, what are you talking about? What does this have to do with anything? And I'm like, okay, hang on with me here. What we're ultimately trying to get to is an understanding of percentiles. And let me go to this one. Okay, the reason we're doing this, and I'm going to show you in examples probably next week, is that we want to learn about what the percentile is and ultimately what a standard score is. That's the whole reason for going from data to the mean or central tendency, to variance, to standard deviation, ultimately to percentiles and standard scores, because those mean things that people can consume. That's ultimately the bread that came from the flour and the dough and all that stuff. Okay, so now let's look at this chart. If we know that we have a normal curve here and we can assume our average is 80 and our kid scored 62, we're down in this range, all of a sudden we can go down here and we can talk about percentiles. Now, the way percentiles work is a percentile is a score from 0 to 100. And if we were to take everybody in an entire class or entire distribution, we could say, if we lined up 100 people in a row based on the order of their scores, we could say that our kid, and we're just making rough estimates here, if he scored 62, and we know that number was, sorry, I'm doing a lot of flipping back and forth. I apologize about this. Where are we? If we know that number was halfway between this part of our distribution, and we do the same thing here, we could go down here and say he scores somewhere in the roughly 6th percentile. And what that means is out of 100 people, 6% would be lower than him, and 94% would score higher than him. Okay, let me try that again. Percentiles mean if you spread out all the scores, and they scored in the 6th percentile, that means 6 students would score lower on that test, and 94 would score higher. Now just take example, let's just use a quick example. If I scored in the 40th percentile, that would be right here, that would mean it's pretty close to average. And by the way, 50 is average because 50 is in the middle of 100 and 0. If I were to split these numbers up, I could actually put in the distributive scores, and 80 being the smallest and the highest and the lowest numbers being on the edges. We're not going to do that, but I could do that. If I said the 40th percentile, that means 40 out of 100 students would score lower than him, and 60 would score higher than him. Okay, so we're going to use more examples, and we're going to talk about this in much greater detail in a little bit when we show actual scores. But that's what we can understand, okay? So if you got really confused about what I was saying with percentages and normal distribution and the percentage of people that's okay, because that part is a little confusing. But once we know how to interpret a percentile, we're in much closer to the territory of making this useful for us, okay? So I'm going to go back here one more time. And now that we look at this, remember when I said, we don't know if this is out of 100. We don't know if it's out of 86. We just don't really know what the scale is. But even if we don't know what the highest score possible or what the lowest score possible is, we can say, I now understand something about this number 62 that I didn't have access to. I didn't have that available to me before. What I now know is that 62 is a pretty low score. That tells me that only 5 to 6 people are going to score lower than that if I had 100 people on the test, okay? It's clearly the lowest score in the class, but if I were to give this to a whole bunch of people and a lot more people, I could probably get more of an estimate of how low that score is compared to others, okay? And if we really want to do a whole bunch of interesting math, we could say, okay, let's take the highest score. I shouldn't say this isn't really math, but let's just do it for the sake of example. Let's take the score of 92 and we'll go the opposite direction. If we go the opposite direction, we know that 80 is the mean. And if we add 12, because 12 is the standard deviation to 80, what do we get? Well, we get 92. That means that the highest score in the class, they're not way up in this range of super, super smarty pants. They're actually pretty closer to average. They're above average for sure. But how much? Well, they're about 1 standard deviation above the mean. That puts them at, if I were just to kind of guesstimate here, whoops, I guess can't see that very well. If I were to guesstimate here, that's about the 85th percentile, and that means that 85 plus 15 equals 100, so 15% of that population would probably score better than him or her, even though that's the highest score in our distribution right here. But we can't tell that it's the highest, right? Like, remember, we don't know. So hopefully this makes a little bit of sense. Now, ultimately, what we're going to do is we're going to take this understanding of percentiles and we're going to use those percentiles with actual assessment results. We'll get that information later. What we'll also get to is these things called standard scores. And we'll talk about those next time. We're not going to get into that now. I'm going to switch back over to the PowerPoint and talk about some other kind of like random stuff. But ultimately, this is what we want to get to, and we're going to practice this more. So if you're leaving this being like, I don't get it, that's kind of okay. It's not a bad place to be. It's maybe another way to say this, and this is kind of a step out here for a second as I switch back. What my experience, and I hear this from not everybody, but a fair amount of people, is they go through this stuff and they're like, okay, what? There's all these terms and there's all this stuff, and it's very confusing. And then I even go into like all these random extra stuff. And then what happens is that eventually sometimes there's this point where it's like, okay, light bulb. I get it now. I get how all these things fit together and how they make sense. If I've done a decent enough job, you see that progression for this basic stuff into the numbers we're trying to get to. And that's great, but there's so much more, and things just kind of fall into place, and light bulbs go off later. And so if you're at this place of like, it's just kind of I get it, but kind of I don't, whatever, don't worry, because that's an okay place to be. It's uncomfortable, it's frustrating, it's all those things, it's kind of annoying, and you might be like, well, he sucks as a teacher, or this stuff is hard and I want to give up. Don't have that flight response, he sucks, or I want to give up. Fight, flight. Don't have either of those responses. If you can help it, say, I'm going to sit in this uncomfortable place of unknowing and confusion, and I'll do my best to just wait for those light bulbs to go off, because they will, or they might. That's the ideal, hopefully the ideal way to approach this, I think, especially as we move into next week when we talk about actual scores. Okay, but let me just polish off this lecture by talking about some of these other things here. I mentioned already at the outset that some of these things we'll talk about a single variable, like a test score in our example we just used. And other things we're going to talk about, particularly as it relates to research, we might talk about multiple variables, or maybe we'll just use 2 variables for our time, or for our purposes here. If I have 2 variables, like if I give one intervention and I measure depression, well, depression ultimately would probably be kind of high. And then I give an intervention and it goes lower, another intervention and it goes lower, another intervention and it goes lower, until ultimately I've given some treatment and a person gets cured or healed, or whatever you want to call it. That's called a correlation. It means that there's a correlation between my interventions and the reduction of depression. There's some association with those two. That would ultimately be a positive thing, right? I mean, like, that would be a good thing for people in terms of counseling. However, so 2 variables, that's what correlation means. However, the tricky thing is about science is we got to get out of the habit of thinking about good versus bad in this moral sense of like interventions of reduction of depression. That's a good thing. What we want to talk about more is the direction of the relationship. Okay, so this is another thing that gets a little bit confusing for people. The direction of relationship says more about it says more about what the relationship is than whether it's good for us or not. So actually, I'm going to pause the recording here and come back in a second with a whiteboard. I'm going to give you an example. Okay, I forgot that I can't use a whiteboard on my computer right now, the one that I have in front of me. So I'm going to do this. I have a blank piece of paper, or blankish. It's the back of something else. But let's say I have a graph right here, and here are my interventions. So we'll call it Aaron's treatment. TX is an abbreviation for treatment. ATX, we'll say that's Aaron's treatment. And ultimately, we're going to measure depression, okay? So a person comes in, session number 1, and I know my handwriting is terrible, sorry. Session number 1, they have really high depression, okay? Scoring high on this depression scale. After the second session, that depression starts to go lower. I'm going to use dots instead of X's. After the third session, it's lower. Fourth session, it's lower. Fifth session, it's lower. One of the things about correlations that's so helpful and interesting is we can then do some of those. Remember this term inferential statistics? We can infer something about, well, what if I gave a 6th session? Maybe I can do that. And this is not 100% accurate science too. There's other things called regressions that are do more for predictive stuff, or that do that prediction for us. Correlations we can't, but let's just kind of all lump it together just for the sake of understanding here for the basics, is that if I wanted to know what's the 6th session likely going to be, you might recall this stuff called slope that you were able to figure out when you were younger and you were looking at graphs. Well, if I draw a line here, I can say there seems to be some relationship between these. And by the way, they're never going to be fully on the line, but maybe this one's a little low, this one's a little high, this one's low, this one's right on. But if I take the average of all those, because remember, I took the distance from the mean, this would be the mean, and there's some at the distance, and then I do a bunch of math to it, I'm going to be able to find out a correlation number, right? And what that number ultimately is, now let me switch back to, so much switching. That number of correlation is going to be somewhere between the range of 1 and -1. And the closer to 0 that we have, that means if it's close to 0, there's not much of a relationship, not much of an association. But if it's close to this 1 or -1, that means that there's probably a strong relationship between these variables. Now, what was this stuff about positive or negative that I just talked about? And I'm watching the time here, and I gotta hustle up here. Well, one of the things we know is that as the interventions go up, the depression goes down. That's what's known as a negative relationship. Let's quick look at something that we can call a more positive relationship. Let's say we have Aaron's treatment, and this time instead of looking at depression, we're going to look at resilience. And we say, okay, that same depressed person, they came in, and boy, they're just not very resilient at first during this first session. But by session 2, they're a little bit more resilient. As their depression goes down, their resilience goes up. This is what we call a positive correlation. That means as one goes up, the other one goes up. And so this one right here is going to be somewhere in the range between 1 and -1. And that -1, that negative in front of the 1, or whatever the number is, that tells us that there's an inverse relationship. As one goes up, the other one goes down. And when we know what the variables are, we can know something about the direction of the relationship. That's what that means. Same thing here. This one is a positive relationship, so it's going to be somewhere between 0 and 1. We don't know how much they're related, but we at least know they're related somehow and what direction we can assume this graph is going to be going. Oops, I'm off the charts again. Sorry. Okay, so now with that, let's try and finish this off here. So correlations have direction, positive or negative, and they also have strength, which is the closer to 1, the stronger the relationship. That's what that means. Or the closer to -1, the stronger the inverse relationship. So they're always going to fall somewhere between -1 and 1. By the way, this is one of those things you really need to know for national testing because these are concepts that might come up on your NCE exam if you take that. Okay, what is this thing about Pearson's R? Well, anytime you see a small italicized R, like this one here, there's a better one right by my head. Anytime you see this, that means you're talking about Pearson's correlation. Why Pearson? Because it was a dude who found out some stuff. He's the guy who came up with this. So he gets to claim the title of, I want to be italicized